I know.
All right. Yes, happy Friday.
Yay!
Isn't that a good thing? There's no homecoming this week? Anybody in cross country get to go to San Luis?
Yeah.
It's pretty up there. You're gonna pass by my hometown. Okay. If you drive by Santa Maria, just say hi. They were there.
Good strawberries. Very good strawberries.
And Pismo Beach. Oh, so nice. All right. Section 3.1. Whatever your feelings have been about exponential and logarithmic functions, I hope and I pray that we will change them, or at least make them positive if they have been negative in the past. Because with exponential and logarithmic functions, even more so than with anything else we've talked about this year, there are rules and there are systems, plans of attack that you can always take that will work out. But you might have to do some memorizing, you might have to do more studying than you've done before. But I think this year you have to do some studying for your math, right? You have to be using notes a little bit in homework, maybe. You have to be kind of looking over the notes to study to do well in the test. If you're not going over your notes, maybe it's not going so hot. So this chapter is no different. Okay, we're going to have to do some studying. We're going to have to make sure that we understand the plans of attack for how to deal with exponentially things and logarithmic things. We have some formulas, some properties. So let's go ahead and get into it. But guys, it's really not that scary, okay? They all follow a system. They behave in a certain way, and so we can use that to our advantage to be able to deal with them. But first of all, in your calculators, you guys were looking for different buttons that show exponential and logarithmic stuff. Who can show me one of them, or tell me one of them?
Log.
Oh yeah, that's a thing. Where's the log button?
Right next to the 7.
Right next to the 7. And what does it mean? Any log?
Log base 10.
Log base 10 is called the common log. Log base 10, but is there a 10 on there? No. Why? Common log, it never shows the base. It just shows L-O-G for log. Okay, what other buttons on there?
Math. And then go down to A.
Yeah, if you go math and then go down to A, if you have one of the cool updated ones, sorry, the ones with the old buttons are not going to be there, but it says log base. If you hit that button, what do you see? Math down to A. Log base. You can change it. So it shows L-O-G, but then it shows a little, what's it called, a subscript, right? And you can put in a 3 for log base 3, or a 2 for log base 2, or a 7 for log base 7. So you have options of doing other log bases. Hold on, but isn't there another log button in your calculator? Who's LN? Log base E. It's called, anybody know what it's called? LN's LN, but what's his name? He has a base of E. LN actually goes NL. Natural log. Natural log. He starts with an L, I think, just because he's a logarithm, and I don't know. Start with an L because he's a logarithm, but he's a natural log. He's a log base E, and E is called the natural number. E is called the natural number. We'll write it down soon. But LN is also a log. He's just a different log. So if you were to test it on your calculator, are you ready? Did you find the LN button? Where is he? Below the LOG. Why don't you go ahead and take ln of 2. Do ln of 2. And then, you might as well run someone's. Go ahead and do your math and then A. And I want you to get to log with a little base. And I want you to put an E in there. Wait, E? Is that a thing? Yeah, where's E on your calculator? How are you going to put him in there? Yeah, right by the comma, second comma. Do log with an E of 2. Do log base E of, and then put in the argument 2. Same thing? Oh, wrong E. No, not above the 7. Sorry. Where is it? It's a lowercase thing.
Is it above?
Oh, above the divide. Above the division sign.
Oh.
Log with a little e. Sorry. I didn't think of log.
So you want that to be a subscript?
Log? Yeah, with a subscript of little e. And then of 2. Because we did ln of 2. Now do log with a little e and of 2. It's the same because ln means that log right there. But he's so special, he has his own little notation of ln. He's still a logarithm. It's just a log base e. Do you guys find any other exponential buttons? We found all the logarithmic ones. Any exponential ones? Exponential. Maybe we should talk about what the difference is between logarithmic and exponential, and then we'll get back to it. Because believe it or not, look at section 3.1. Even though the chapter says exponential and logarithmic, 3.1 is just who? Exponential, and they're the ones we're kind of like, wait, what? Okay, here we go. Last chapter, we talked about what kinds of functions. Believe it or not, they were called algebraic. Algebraic functions. Algebraic functions. The polynomials, the rationals. There was no trig in there. There were no exponential or logarithms in there. It was just algebraic. Now, there were harder and easier ones. Polynomials were all in one nice line. Rational had denominators, which means they were asymptotes and wholes and all this stuff. But they were algebraic functions. This chapter, they have a special name. Exponential and logarithmic are called transcendental. You want to think they transcend the normal properties of algebraic? They're their own guys. In some ways, they might be related to algebraic functions, and yet they have their own properties. They behave in their own ways. They have their own graphs. Doesn't mean they can't have a vertical asymptote or they can't be an irrational function. But the rational functions we saw were just f of x over g of x, where both f and g were some sort of polynomials. Maybe just a constant. But that would be a monomial, right? Maybe a binomial, maybe a trinomial, maybe a quadratic or a cubic. But we didn't have anything else funny going on. So rational functions actually are a broader category, but the only ones we saw were algebraic ones, which is polynomials on top, polynomials on bottom. But these new ones, exponential and logarithmic functions, are called transcendental. And just to show you a basic one, y equals a to the x, or you could say, and I tend to say, because I like it a little bit better, b to the x, but maybe you won't like it because the book doesn't always do it. I use b for base. Y equals b to the x, base to a power. And logarithmic, y equals log base b to the x for base. Hey, those b's are the same. Well, kind of, they're a little bit different. And if you want to be super snazzy and review some things from last year, if these two were related, this is the general function. The general function is you're given an exponential and the x is going to be up there. And a logarithmic, you're given a function, the x is going to be right there. But if we were to relate these two together, we could actually rewrite this and say, hey, because these two are related, they're actually inverses of each other. We'll talk about that as we go on. But if we were to relate these two, does anybody remember how to go from logarithmic to exponential and back?
Isn't it like x equals
X does equal base.
oh yeah, y is always the exponent.
A logarithm is an exponent. It's just kind of like, don't worry, we're going to talk about it, we're going to do examples, it's going to be in its own section. But if it does help, just to kind of be like, oh, I think we did this. Yeah, you did. You did. But it's easy to forget. But technically, from my remembering of it, even though this is good, and even though this is totally right, I would write it the other way, because I would start with the b, because the base of the log is the base of the power, and then I just think back forth. Start with the base, you have to go across the equation to get the power, and then you come back to get the other side. But that's just, I don't know, that's my silly brain making a way of remembering. Maybe it doesn't help you at all. But I always say base to base, and then go back and forth. Base to power equals. But that's just me. Okay, let's talk about exponential functions. Alright, as I said, the book uses an A. I like a B because B is the base, whatever. So I'll use what the book uses just so that you won't be surprised when you see the notation. F of x, that's a function, right? Equals a to the x. Exponential. exponential. Let me describe exponential for you. Constant base variable power. Exponential functions. Constant base variable power. Constant base variable power. Constant base variable power. Who's my base? A. So what am I going to write next to him? Constant. And by constant, what do I mean? He's a real number. Technically, greater than 0. Because if he was 0, 0 to any power is 0. Almost. 0 to 0 doesn't exactly work. He's like 0 over 0. He's called indeterminate. That's for another day. Why don't I say negative ones? Negative 2, negative 3, negative numbers? Why not? We'll look at it. Negative numbers cause problems. They don't behave like exponential functions. Because a negative number, 1 second he's negative, then he's positive, then he's negative, then he's positive, then he's negative. He bounces all over the place. He doesn't move smoothly. So exponential functions are defined only for a positive, constant basis. Who's x? Power. Raised to the power of, right? He's the power. I guess we could say raised with the exponent. We could say he's an exponent too. So, cool kids. When I asked you on your calculator to figure out exponential functions, there was really only one button to find. There was really only one button to find. Did you find it? Yeah, the caret. Okay, there's 2 buttons. The caret. But there is one exponential function actually on your calculator. Can you find the one that's actually there? The caret lets us make exponential functions. Lets us plug into exponential functions. So it says, hey, somebody to the power of. But there's one. You don't have to go looking in the menu. He's right on the above the ln. What is it? It's e to the x. Good. Good. He's the one exponential function that you'll find. Now, coming back. So if there's not a button for 2 to the x, how do we do it? What Luke said, we gotta use the caret. It's the easiest way. You could go, I think there's something in the math menu that might help, I don't know. It's kind of lame. Just use the caret. So when we want to find a, we can go ahead and say f of negative 3.1. Wait, why am I putting negative 3.1 in the parentheses? I'm plugging in. If I plug in there, where else do I plug in? Hey, whenever you raise a number to a power, it gets bigger, right? Go. Whenever you raise a number to a power, it gets bigger, right? Go. What do you get? 12. What? Point? Isn't he smaller? We'll talk about that, but go ahead. Point what? Okay, so you're done with that. What on earth made him smaller? Negative power. Do you remember what a negative power does? A negative power says, hey, you're not where you belong. You belong down here. Ooh, 1 over 1 divided by a kind of big number. Yeah, that would be a small decimal, yeah? So just something to keep in mind. Exponential functions don't always grow. If their powers are negative, they're going to shrink. So then letter B, just to further practice real quick. F of pi. What? Oh, pi's a number. Yeah, that makes sense. F of pi equals 2 to the negative pi. What do you guys think? Is it going to grow or is it going to shrink? Yeah, it's going to shrink. We'll go ahead and plug it in. Give me a decimal real quick. Point. 1133. We could round it. I just decimals. Why are they so close? Oh, that's right. Who is pi again? 3.1415926, etc., right? Okay. Exponential functions. They grow as long as their powers are positive. They shrink when their powers are negative just because of the nature of exponents. Ah, stink. We're going to have to reveal those exponent rules, aren't we? But hold on, before we get there, let's just talk about his graphs. His graph. The general exponential functions graph. So general exponential function, let's just use who we had. But can I go ahead and use my b just because I like him better? Okay, y equals b to the x. As long as b is, which, guys, I'm not going to write this every time. It's actually kind of a definition of an exponential function. But b is always greater than 0 in case you need that. If I was to plug in stuff, for instance, if I was to plug in 0, what's b to the 0? If b is greater than 0. Any number to the 0 power is weird, right? But yeah, true. 1. So then I can say any exponential function that hasn't been transformed, the parent function. Aw, stink, is that what we're doing? The parent function of exponential functions will have a point at 0, 1, whatever the base is. 2, 3, 7, 11, 8, 10, pi, whatever it is. Will have an intercept at 0, 1, because when you plug a 0 into the power, the entire thing becomes 1. Now what if I plug in 1? Well, b to the 1 is b, right? It'd be whatever number is in the base. If I plug in 2, now it's b squared. What's going on to b? He's growing, right? Let's go on to my function, he's growing. However, that's not going to quite be accurate. What's going on as I start plugging in those negatives, remember? Negative 1, b to the negative 1, who is that really? 1 over b. So if it's 2, that'd be 1/2. If it's 3, it'd be 1/3. If it's 4, that'd be 1/4. If it's 10, it'd be 1/10. Oh my goodness, it's getting small. If I plug in negative 2, now it'd be the negative 2, which would be the same thing as 1 over b squared, and it's even smaller. What's it doing? Shrinking. And it's going to keep shrinking. But even when I have 1 over b squared, 1 over b cubed, 1 over b to the 10th, 1 over b to the 100th, it never goes negative. It just gets tinier and tinier and tinier and tinier and tinier. AKA closer and closer and closer to 0. AKA, I know we haven't gotten there yet, but isn't there a horizontal asymptote? It doesn't have to go both ways. One direction, going to the left, it's going to approach y equals 0. So there's a horizontal asymptote at y equals 0. It only opposes it, though, to one side. So let's talk about its behavior. It's kind of weird, right? Horizontal asymptote, but it only goes that way one direction? Yeah, he's not a polynomial. We're in a whole new world. Domain. What do you guys see? How far left does he go? Yeah, he goes negative infinity. How far right does he go? Infinity. Perfect. Range. Remember our questions? How low does he go? Greater than 0. So who would be my lowest point that I'm going to put? 0. But I have to make it what? Open. Because it's going to, 0 is the boundary. It's going to get closer, 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 but never hit. Remember, open means open circle. How high is he going to go? Yeah. There you go. You got it. Infinity. Yeah? How low does he go? 0, but never hitting. How high does he go? He just keeps on going to infinity. And actually, exponential growth, this is something like if you're listening to like commentators or something in like the business channel like, or in CNN or something, or they're talking about some problem that's getting out of control, they're like, it's growing exponentially, right? It's because exponential growth is one of the fastest. It's one of the fastest. It could be 2. 1 doesn't really work either, to be honest. At least not super well, because 1 doesn't even parallel just be itself, right? So it's kind of like b greater than 0, and technically we usually say b not equal to 1, but they won't have b be 1. If it is, it's lame and boring. It's just a y equals 1. But I guess you could say 2 to the x. The problem is you could actually have 1/2 to the x, so it's kind of like, where do you start? I don't know. Y-intercept, we already talked about him. When x is 0, when the power is 0, it's always going to, the function's always going to be 1. Strictly monotonic. Do you remember what that means? We talked about it. Why is he strictly monotonic? What is he strictly doing? Strictly increasing. Remember, we read it left to right? So we can say strictly increasing. Strictly monotonic. Monotone, it's only doing one thing. It's only increasing the entire time, right? Strictly increasing. Which means all of his differing slopes would be positive, right? Not just positive, but getting higher. And then continuous at the last thing. There's no vertical asymptotes. There are no holes, no breaks in a normal exponential function. Now, if you put him over an x or something, well, all of a sudden, yeah, he's going to have all that extra stuff. But he in and of himself, this function in and of itself, is not going to have any breaks, any holes, any problems. So the nice thing is, any domain restrictions just from him? No, he's fine. No domain restrictions. He's good. Logarithms are another story, but we're not doing that today. Whew. Let's keep going. Good? What's this page say? It can be transformed, but it's okay. We got it because we've done transformations, right? Yeah. Does anybody notice anything missing? I have additions outside. I have addition, or whatever, subtraction inside. Huh. What don't I have? Reflections, we're actually going to talk about because there could be negative numbers. But I don't have any dilations, huh? I'm not saying it can't happen. I'm just saying it's not very common that it would happen. We might look at dilations, but it doesn't really make a huge difference. I'll try to show you why. But first of all, let's start with what we do see. You guys right now are writing one version of a transformed exponential function. Does it look funny? Yeah. Yeah, it does. But let's see if we can still do it. If there is, can you guys find the parent function? Where is he right now? Here he is, right? Okay. Here's our parent function. What's going on with b? What would that make if I'm adding a b on the outside? Vertical. Shift. Why vertical? On the outside, and when it's on the outside, it's strictly affecting, imagine this is y. The y's, the original function y's are being increased or decreased, depending on whether b is a positive or negative number. So b is going to be a vertical shift b. You thought I did not leave enough space. B units. So if b is a positive, oh, hey, it's going to be a shift up. If b is a negative, oh, hey, it's a shift down, right? A, we'll get back to that in a second, but we've already named him. Who is A? He has to do with the parent function. He's just the base, but he actually can change things. If A is 2, or if A is 3, or if A is 4. I can change what's happening with my function. We'll talk about that too. C. He's on the inside, right, guys? Look at that. He's right next to X. What kind of transformations happen right next to X? Addition or subtraction? Good. Horizontal shifts. C units. But what do you see before the C? A negative. So it's going to be opposite of what you think. If it's X minus C, you're moving C units to the right. And if it's X plus C plus a positive number, there'll be C units to the left. Right? Reflections. How is a reflection going to show up in an exponential function if it's across the x-axis? You guys remember which one that was? Across or about, or it could say at the x-axis. What kind of flip is that? Up, down, right? Vertical. So that means there has to be a negative on the, on the outside. So I would have my function y is equal to, for sake of just making it simple, let's just say there's going to be a negative in front of the a to the x. There's going to be a negative in front. And then if there's a reflection across the y-axis, or it could say about that y-axis, or at the y-axis, whatever. That's going to be a back-forth, a right-left, a horizontal reflection, which means where's that negative going to appear in our parent function? a to the negative x, right? If the negative is on the inside, that's a horizontal flip. And then if the negative's on the outside, that's a vertical flip. Are we doing all right? Are we still awake? Still alive? Okay, it's Friday. Okay. Good to keep going? Let's practice. Yep. First of all, though, do you guys see an e to the x? Can you graph it real quick? Let's see what e to the x looks like. Now, you won't believe me. But you can ask any calculus kid this year, A, B, or BC, to see if I'm right. Why am I showing you an example with e to the x? Because eventually e to the x is going to be one of your best friends. In calculus, if you see e to the x, you're like, oh, praise the Lord. I'm glad it wasn't a 2 to the x. So I'm just using e to the x to say, hey, he's a guy, he's a thing, and he's going to be helpful one day. That's all. What's he look like? Normal e to the x. Didn't he look kind of like the other one? Huh. Well, that's not very exciting. He's still going to hit where? Did you guys figure it out? Wasn't it 0, 1 still? Huh? Yeah, it's probably a good idea. It's a good example. E to the x is still going to hit at 0, 1. But the weird thing is, where is he going to hit when x is 1? Plug in 1 to e to the x, and what do you get? E to the 1 is e. Uh-oh, struggle. Who's e? What is e? I'm going to write it real quick. The e, the number, is approximately. I'll search it out. 2 point. How can you figure it out? Hit the second division sign, enter, or hit the second ln and then make it to the power of 1. What do you got, Luke? 2 point? Yeah, cool. He's just like pi, and then he goes on forever without having a pattern. He's called irrational. He's important in lots of ways, but we won't get to them today. So where would I put the 1? Let's do 3 and go down a little bit and just say, hey, you're e. Yay. Okay, whatever. So, but otherwise, he looks kind of like the other exponential function, right? The one that we showed in the page before. So question, what's going to happen when we look at g? Now, can anybody quickly remind me, why am I getting a couple points to help us out? Is it easier to move a whole graph or to move a few of his points? Yeah, a few of his points and then connect, right? Okay. So, what's going on in G? Left down, hit my red marker wherever I left it. There it is. Plus 3 on the outside. Okay, it's going to be a vertical shift. But then we also have, ooh, a negative on the inside. What is that going to do? Flip, oh, which one? Across the y is going to be a horizontal flip. Oh, does it matter if we go up 3 and then horizontal flip it, or horizontal flip it and up 3? Doesn't matter, whatever order you want to use. I'm going to go ahead and flip it first because that seems kind of easier, so I'll go -1. I'll flip it, that one's going to stay the same. Then I take each of these points and I go up 1, go up 2, go up 3. And I go up 1-ish, 2-ish, 3-ish. Wait a minute. Who else is kind of important for e to the x? The y-axis is kind of important. He's the horizontal asymptote. He tells me how low to go. So I need to shift him up a 1 and a 2 and a 3 as well. Then I know. Whew, there we go. That was a little rough. Then I know where he's supposed to be approaching. So for exponential functions, it's going to be helpful not just to move points, but to also move the horizontal asymptote. That way you don't randomly just have like some little line thing going on that doesn't really show an exponential function. Now, struggle. How about h of x? What's going on there? Okay, I'm going to write this because there's a lot going on. I do have a vertical shift, and technically, careful, don't look here. Look here. Wasn't there a positive 1 that was put in? So I'm going to have a vertical shift, what? Up 1. What else am I going to have? Good. Horizontal shift left. Why left? He's positive. Oh, that's right. Backwards what I think, right? Left 2. Uh-oh. What else? I have a negative. You guys see him? Yeah, he's going to do a reflection across the x-axis, or I could say a vertical flip, just for the sake of being fast. The short and sweet. Now, do you guys remember what I should do first? Should I go shifting him all over and then do flipping? Or should I flip first and then go shifting all over? Flip first. So I'm going to go ahead and flip first. So instead of being up, what's he going to be? It's going to be down. 1 and a 2 and a 3. There's our E. Okay, so that's where he is right now. But now what else do I have to do besides move him, besides the vertical flip? That's a check. Okay, vertical shift. Can I do both of these at the same time? So I'm going to go up 1, and then left 1, 2, right? Okay. Then I'm going to go up 1, and left 1, 2. Okay. And then, wait, where's my horizontal asymptote? Okay. Move him up 1 and left. Wait, does it matter if I move a horizontal asymptote left? No. Where'd he go? Up 1. Then go ahead and say. Sweet. So I move each point up 1 over 2, up 1 over 2. Then I move my horizontal asymptote up 1 over, well, he just goes the whole way anyway, so it doesn't really matter. But do you kind of see how the technique has changed a little bit with exponential? We don't need tons of points, but we do need at least a couple. The intercept is a good one, and then plugging in x is 1 is a good one to use. We know the curve, we know the shape, but we also need to move that horizontal asymptote or else it gets kind of tricky. Is that okay? Kind of? You're going to be able to practice this a little bit more in homework, but at least we have the idea of how transformations work for exponential. I know, you're all groaning, but we haven't learned the logs yet, and for some of you, you're like, oh, it can't get that bad. If you don't know that, we're not learning logs yet, so they haven't gotten that bad yet. Once we learn logs, these will get worse. But right now, since we haven't learned logs, we get to use this cool property called the one-to-one property. We get to use this cool property called the one-to-one property. We're almost there. This is the second. We have 2 more slides. This one and 1 more. The one-to-one property. Without logs, without using any logarithms or putting in any logarithms, we can only solve exponential functions set equal to numbers. We can only solve exponential functions set equal to numbers if we can make the bases match. Without logarithms, we can only solve exponential functions if we make, and I mean by hand, if we make the bases match. Because if we can make the bases match, we can use the property that says, if the bases match and they have to be equal, the powers must be equal as well. If the bases match and the 2 expressions are equal, then the powers must be equal as well. But the struggle is, guys, look at both these examples down below. Do either of them have matching bases? No, this one's 2 to the 2x, this is 64 to the 1. They don't even match. What's the big deal? Yeah, it must be bad at examples. You can split up 64 quite a bit, right? 64, can't I say 64, and can't I say he's 8 and 8? And can't I say 8 and 8 is 2 and 4, and 2 and 4, or 4 and 2 either way. And 4 is 2 and 2, and carry that one down. Now some of you guys use boxes for this. Did they ever use a box when they were trying to find all the prime factors, right? You can keep on going like this. Keep on going like this. Whew! Either way, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Whether you use the factoring tree or the box method, you can say 64 is the same thing as 2 to the 6th. Why is that so stinking helpful? Yeah. Bases are matching. So these are like the easy problems because you say, oh, sweet. If the bases are matching, you can say, hey, your power, 2x, is the same as your power, 6. The bases are matching and they're equal expressions, then I have to set the powers equal to each other, and then all of a sudden it's easy because x must be 3. I'm not saying that's the easiest it gets, but that's pretty close. The next one gets just a little smidge harder. Because there's a 1 over and we don't like that. But did you guys see me today go from something to a 1 over? And in comparison, we could maybe go backwards. How did I do the 1 over earlier? What were we doing? There was a negative what? Power. What's the power of 125 right now? 1. So how could I rewrite this without the 1 over? Oh. Now, am I all the way to using this property? No. But 5 and 125 look like maybe there's something going on, yeah? So if we were to take 125, and if we were to break him down and say, hey, let's figure out, take 5, we get 25, take another 5, we get another 5, take another 5. Oh. Who can I rewrite 125 to be? Now, hold on. It's a bit of a struggle. Some of you might get here faster than others. What do I do when I raise a power to a power? I multiply. So I can say 125 to the negative 1 is the same thing as 5 to the negative 3. And you can check it. You can say, hey, if I do 1 over 5 cubed, who is 5 cubed? 125. Oh yeah, it works. But who's on the other side? Why is life not good? Bases match, so the powers have to equal. Bases match. In the equation, powers have to equal. When you solve for x, oh, it's a little baby algebra one. Isn't it cute? X equals who? Negative. How do we do? Okay. What's a general technique? If you see any 1 overs, try to make them all in one place, in the sense that, you know, 5 doesn't have a denominator. We don't want 125 to be in a denominator. So if we need to, go to negative exponents, then take the bigger number and see if he breaks down to be the same base as the smaller number. Our hope is yes. But just a warning, there are worse ones out there, and we need logarithms for them. Let's go and take a quick second and talk about E. The nice thing is, though, I already introduced him to you, so maybe you're not as scared of him as he might have been. Let's talk about E just for a second. E, his name, natural number. Weird, but true. His value, 2 point. Do you remember?
7182.
I think so. We wrote him somewhere. Too far. Yep. Oh. I put that in the wrong spot. Can you see it? Oops. Natural number is E. I don't know. I just wrote it twice. Whatever. Natural number is E. What was the answer? E is the natural number. E is approximately 2.71. You could do all the decimals, but kind of like pi. Pi is 3.14 for a lot of us. We could say, I suppose, E is approximately 2.722. I'm going to keep 718 just to be a little more precise. The exponential function, why is he exponential? Because E is a what? Constant. So E is a constant base. I do have my constant base and my variable power. So yeah, he's exponential. Now E is like pi in that there's like a symbol for him, but he represents an actual number. So yeah, he's a constant. Oh, you guys gonna get scared when you see E? How are you gonna solve? Same base. Doesn't matter that it's E, right? So it's the same base. How do you solve? Using the 1-to-1 property. No need to be afraid, right? So Subtract the 2, we get 1. Divide by the 3, just for sake of time, we'll just do the algebra fast. 1/3. No big deal. And to be honest, what makes this one tricky could be just as tricky if you had 2 to the power of it. It'd still be hard, because what are we supposed to do now? 1-to-1 property, bases are the same? Just a few of you are like, oh, stink, how do you solve that? But hopefully others of us could chime in and say, oh, it's just a polynomial. We just need to get polynomials all to one side. And then say, oh, sweet, guess what? He's a quadratic. That, by the way, has some very nice factors. Look at them sneaking in some old factoring practice in the midst of exponential solving. That's okay, you can take it, right? Cool kids, guess what? Not bad. Hopefully not bad. Homework due on Monday, you guys got it. Homework number 18. Have a great weekend. Try to find some time to rest your body, your mind. Recharge a little bit, okay? Hang in there, kiddos. Happy Friday. Yeah. Sorry, kid, I ended up teaching the whole time.